Picture the scene. It's late, the rest of the house is entirely quiet.
Just you and the hum of the fridge.
Exactly. The streetlights outside are flickering, and your main source of illumination is just that harsh, unforgiving glow of your IDE in dark mode.
A very familiar setting for a lot of you listening, I'm sure.
Oh, absolutely. And you're staring at your terminal, nursing a cold cup of coffee, trying to figure out why the large language model you just integrated into your app returned a response that is so bizarrely illogical.
Like it's actively mocking you.
Right. You gave it a simple set of rules, a perfectly straightforward logical deduction task, and it just completely faceplants.
That happens all the time.
And you're sitting there thinking, you are a machine.
Yeah.
You are literally built out of silicon and math. How are you so bad at logic?
It is a totally valid question.
Well, welcome to the deep dive. Tonight we're turning down the lights and turning up the analytical rigor. Consider this your late-night debugging session of the AI mind.
It's the perfect setting for what we're about to explore, really. Because that frustration, that specific late-night developer frustration, it stems from a very fundamental mismatch.
A mismatch between what we think is happening and what's actually happening.
Yeah, exactly. Between what we assume a computer is doing and what a neural network is actually doing under the hood when we ask it to reason, we project our understanding of traditional software architecture right onto these models.
And to figure out where that cognitive mismatch comes from, we are unpacking a massive stack of notes tonight from the LLM Mastery Deep Dive.
Specifically, their material on logical reasoning.
Right. We're looking at deduction, induction, and just the deep, sometimes maddening architectural quirks of how artificial intelligence processes logic.
It is a wild ride.
Because, as software engineers, you deal in strict Boolean logic every single day. True or false? If this, then that.
You live in deterministic systems.
Exactly.
Yeah.
So naturally, you assume that a massive computational machine would be an absolute master of cold, hard deduction.
You assume it processes logic the way a compiler parses code. Like, if the syntax is valid, the execution is flawless.
But language models are not compilers.
No, they're not. They do not execute instructions. They approximate patterns.
Which means the reality, according to these notes, is completely inverted from our baseline expectation. They are actually surprisingly weak at strict deduction.
Yeah, they really struggle with the kind of rigid logical frameworks that, a simple Python script just executes effortlessly.
And instead, they excel at something entirely different. So to understand why they fail at those basic logic puzzles you throw at them in the terminal, we first have to map out how they handle reasoning.
The three main types, right? Deductive, inductive, and abductive.
Right. And the architecture of a transformer model really dictates its strengths across those three types.
Yeah, the sources point out that language models handle these reasoning styles with wildly varying degrees of success. And that variance tells us everything about how they're built.
Okay, let's unpack this. Because the biggest surprise in the notes is that LLMs are at their absolute weakest when it comes to strict deduction.
Which is so counterintuitive.
It really is. Deduction is applying general established rules to reach a guaranteed specific conclusion. A equals B, B equals C, therefore A equals C. It is airtight.
But the sources say LLMs are actually strongest at abduction.
Right. And for anyone unfamiliar, abduction is formally defined as inference to the best explanation.
Right, it's an educated guess.
Yeah, exactly. For the engineers listening, think about it like debugging a massive, undocumented legacy code base. Deduction is what you do when you trace the code line by line.
Stepping through the debugger.
Watching the variables change state in memory so you know exactly mathematically what is happening. But that is not what the LLM is doing.
Not at all.
Abduction is when you just glance at a massive, cryptic stack trace, look at the timestamp, notice the server load spiked, and intuitively guess, it's probably a race condition in the database.
You don't have the mathematical proof yet.
Nope. But it is the most plausible explanation based on the surrounding context. LLMs are those intuitive guessers. They are not the line-by-line tracers.
What's fascinating here is why this happens at a structural level. If you look at the core mechanism of a transformer, abduction makes perfect sense.
Because of how it processes context.
Exactly. Abduction requires synthesizing a massive amount of surrounding context to find a highly plausible explanation.
Which is what transformers do best.
Right. That aligns seamlessly with the attention mechanism in a transformer. It's designed to look across a massive context window, weigh the relationships between all those tokens simultaneously, and predict the most statistically likely continuation.
So they aren't executing a logic gate at all.
No, they're surveying the semantic landscape of your prompt and inferring the most probable shape of the answer. They guess the race condition because mathematically that cluster of symptoms usually points to the vector representing a race condition.
So they are essentially playing the world's most sophisticated, high-dimensional game of probabilistic fill-in-the-blank.
That is a great way to put it. When you ask them to do strict deduction, to follow a rigid multi-step rule without deviating, you are asking a probabilistic guessing engine to behave like a deterministic state machine.
It's fundamentally the wrong tool for the job.
Yeah. The attention mechanism wants to look at everything at once and find a vibe, for lack of a better word. But deduction requires tunnel vision on a single strict rule.
Well, if the model is relying on the broader context to find the most plausible explanation, what happens when you give it a prompt where the strict logical rules demand a conclusion that makes absolutely no sense in the real world?
Oh, this is a massive roadblock.
Yeah.
They get distracted by their own training data.
The source is called as the content effect, right?
Yeah, the content effect. It's a phenomenon where the real-world knowledge embedded in the model's weights actually overrides the formal logical structure of the prompt.
Meaning the semantic meaning of the words derails the mathematical logic of the task.
Exactly.
Wait, I have to push back on this to make sure we're grasping the actual mechanics here. Because under the hood, a transformer is just executing massive matrix multiplications,
Right, it's just math.
pushing floating point numbers through layers of silicon. It doesn't actually know what a server is or what cheese is.
Right, it has no physical concept of those things.
So if we give an LLM a perfectly valid logical syllogism, structurally flawless but with an absurd premise, like all servers are made of cheese,
Okay, I see where you're going.
the database is hosted on a server. Therefore, the database is hosted on cheese. How does the semantic meaning of a word override the mathematical structure? How does math get distracted?
That is the core architectural tension. You're right, the model doesn't know what cheese is, but it does have vector embeddings.
The points in the high-dimensional space.
Yes, every word or token is mapped to a point in that space. The tokens for server, database, metal, and silicon are all clustered very tightly together because they appear together constantly in the training data.
And the token for cheese is miles away in a completely different cluster.
Exactly. When the attention heads calculate the weights for your prompt, the gravitational pull of those massive established semantic clusters is incredibly strong.
So the connection between server and hardware is just structurally denser.
Deep and dense. And the connections representing the abstract logical structure, like the if, the all, the therefore, are relatively weak by comparison.
Oh, wow. So the gravity of the embedding weights just pulls the calculation off course. The model literally can't separate the underlying form of the logic from the semantic content of the vectors.
Right. The attention mechanism highlights the heavy semantic tokens and essentially washes out the purely structural logical tokens. It cannot unsee its training distribution,
There's like a gravitational anomaly.
dragging the model away from the clean lines of deductive logic, back into the messy statistical reality of what those words normally mean. And interestingly, the sources explicitly note that the content effect is a consistent bias found in human reasoning as well.
That makes a lot of sense, actually. If someone makes a perfectly sound logical argument, but we violently disagree with their core political or social premise, we tend to reject the whole thing.
We do. Our brain refuses to accept the structural logic because the content triggers all our preconceived biases.
So it's cognitive bias mirroring. We struggle to accept logically sound arguments if we disagree with the factual premise, and the LLM struggles to output logically sound tokens if the premise contradicts its training data.
Precisely.
Well, if the world knowledge is getting in the way, why don't we just strip the semantics out? I mean, an engineer listening to this is probably screaming at their dashboard right now saying, just train a model entirely on abstract symbols.
Take the words out entirely.
Yeah, train it on pure A, B, and C logic loops without any real words, so it learns the rules without the semantic gravity.
Researchers do test that, actually, and the results are incredibly telling. When you strip away the familiar words and force the model to reason using completely abstract symbols or synthetic languages, its performance often collapses.
Wait, really? It just breaks.
Yeah. It turns out, stripping the semantics strips the LLM of its primary navigational tool. It doesn't possess a separate underlying logic engine. It relies almost entirely on the familiar shape of language patterns to simulate reasoning.
So without the semantic gravity to guide it, it just drifts.
Exactly.
Well, here's where it gets really interesting for anyone who has ever built a distributed system. If a single step of logic can be completely derailed by the gravitational pull of the vectors, what happens when you try to force an LLM to string together a long chain of logic, like a complex multi-step coding problem?
The degradation is severe. The notes highlight that multi-hop reasoning degrades exponentially as the chain length increases.
Think about multi-hop reasoning like a microservices architecture. Let's say you have a user request that relies on 6 different microservices to resolve.
Okay.
Each individual microservice is highly reliable. It has, let's say, a 95% uptime service level agreement.
95% sounds pretty robust.
It does. But because the user request requires all 6 services to work in sequence, you have to multiply those probabilities. 0.95 to the power of 6. Suddenly, your overall system reliability is only about 74%.
Wow.
Yeah, you are dropping 1 out of every 4 requests. The points of failure compound multiplicatively.
And that multiplicative error rate is the hidden, often ignored bottlenecks in agentic AI and complex problem solving right now.
Because every step is an independent generation.
Exactly. When an LLM attempts multi-hop reasoning, every single step is an independent probabilistic generation. Even if the model has a state-of-the-art 95% accuracy rate per step on a logic task, chaining 6 of those steps together yields only a 74% overall accuracy.
It is mathematically inescapable.
There really is.
You know, it explains the bizarre user experience of watching an LLM write code. You watch it nail the first 3 functions of a complex script, and you think you are witnessing magic.
Right, looks brilliant.
But then, by function 5, it completely hallucinates, forgets the variable scope, and starts importing a library that hasn't existed since 2014.
Because at function 5, it isn't just dealing with your original prompt anymore. It is dealing with the context of its own previous generated tokens. This brings in the concept of autoregressive generation.
Right, generating text 1 token at a time.
Yeah, and every time they generate a token, it gets permanently appended to the context window. They are trapped by their own history.
They build the road 1 brick at a time, but they can never go back and replace a crooked brick.
That's a perfect analogy. If there was a microscopic deviation in step 2, maybe the attention mechanism was slightly pulled by a semantic bias. That deviation is now hard-coded into the context for step 3.
And the context shifts slightly further away from the logical path.
Right. By step 5, the prompt and the generated history are so misaligned that the logic chain doesn't just bend, it shatters.
And the model lacks the deterministic guardrails to step back, realize it took a wrong turn, and rewrite its own memory. But if errors compound that aggressively during generation, you'd think we could just prompt the model to double-check its own work, like build a secondary prompt that says, read the code you just wrote and fix the logical flaws.
You would think so. But doing that exposes a massive architectural gap between reading text and writing it. The sources call it the fallacy paradox.
The fallacy paradox, what does that mean?
It reveals a profound asymmetry in how these models operate. The notes indicate that models are incredibly capable at recognizing logical fallacies as a classification task.
So if you give them a finished piece of text and ask, is there a logical fallacy here, they'll spot it.
With remarkable accuracy, yeah. They can read the flawed logic just fine.
And they still generate it.
Exactly. They are terrible at avoiding those exact same fallacies when committing them in their own reasoning.
So what does this all mean for the developer trying to leverage these tools? It reminds me of the classic senior dev versus junior dev dynamic, but packed into one entity.
Oh, I like that. How so?
Well, the LLM is like an incredibly pedantic, eagle-eyed code reviewer.
Yeah.
It can look at someone else's pull request, the classification task, and immediately spot every anti-pattern, every memory leak, and every logical flaw.
It'll leave 40 comments tearing the logic apart.
Right. But then you ask that exact same entity to build a feature from scratch, the generation task, and it writes absolute spaghetti code riddled with the exact same flaws it just criticized.
That senior dev versus junior dev dynamic is a great way to visualize the difference between bidirectional attention and causal masking.
Bidirectional attention.
Yeah, we have to look at the architecture to understand why reading is so much easier for them than writing. Recognizing a broken pattern, spotting the fallacy in an existing block of text is a classification problem.
Okay.
During a classification task, the model's attention mechanism is bidirectional. It can look at the entire sequence of text all at once. It can see the beginning, middle, and end simultaneously.
So it's looking at a static map.
Exactly. The anomalous pattern, the logical flaw, stands out clearly against the statistical distribution of its training data.
But generating is different.
Vastly different. Maintaining a pristine logical pattern over multiple generated tokens is a completely different architectural challenge. When generating, the model uses causal masking. It cannot see the future.
It has to guess the next step blindly.
Right. It has to autoregressively predict one token at a time, balancing grammar, the context window, the gravitational pull of the content effect, and the abstract logical rules all simultaneously.
That sounds computationally exhausting.
It is. It is vastly more difficult to maintain structural adherence while blindly stepping forward into the unknown than it is to look at a finished sequence and flag an anomaly.
That massive gap between classifying a logical rule and actually executing it sequentially brings us to what the sources highlight as the most fiercely debated question in the artificial intelligence space right now.
Oh, the tension between rules and correlations.
Yes, the ongoing debate is whether these neural networks are actually learning underlying logical rules, meaning they've extracted the abstract mathematical mechanics of deduction, or if they're merely echoing statistical correlations.
Just repeating patterns they've observed billions of times in the training data.
It's the difference between knowing that a certain block of code works because you understand the underlying algorithm versus knowing it works because you copy-pasted it from Stack Overflow 100 times and it usually compiles.
Right. And to figure out which one is happening, researchers probe the latent space. We mentioned high-dimensional space earlier. The latent space is essentially the internal multidimensional map where the model organizes concepts.
Okay, so how does that prove if they know the rules?
If a model has genuinely learned an abstract logical rule, that rule should apply universally, regardless of where you are on the map. It shouldn't matter if you are processing English, Python, or a completely synthetic made-up language.
But earlier you mentioned that when we test them on synthetic languages, they collapse.
Exactly. If we connect this to the bigger picture, the practical implication for the software engineer sitting at their terminal is pretty stark. An LLM's reliability strongly correlates with how closely your specific problem resembles the dense clusters in its training data.
So when you prompt an LLM with a novel, unique logic puzzle or a proprietary architecture problem in your specific undocumented code base, you are not engaging a universal reasoning engine.
No, you are traversing a statistical latent space.
Traversing a statistical latent space, you aren't booting up an arithmetic logic unit. You are wandering through a library of probabilities.
And if the puzzle you present is out of distribution, meaning it sits in a sparse area of the latent space that doesn't look like the millions of examples the model was trained on, the illusion of reasoning drops away.
Because the correlation isn't there.
Right, the model relies on correlation to navigate. When the correlation isn't there, the logic just fails.
Well, we've covered a vast amount of architectural ground in the dark here, so let's synthesize the stack trace of this deep dive.
Sounds good.
We started with the realization that LLMs, despite running on deterministic silicon, are surprisingly weak at strict deduction, the line-by-line tracing, but they are incredibly adept at abductive guessing, acting like a seasoned developer intuiting a root cause from a cryptic log.
And we broke down the content effect, revealing how the heavy vector weights of their vast world knowledge overpower the thin logic of abstract rules.
Making their biases strangely similar to human cognitive blind spots.
Yeah. We also looked at the brutal math of multi-hop reasoning. We saw how causal masking and autoregressive generation trap the model in its own flawed history, turning a 95% per step accuracy into a compounding cascade of failure over just 6 steps.
And we explored the fallacy paradox, driven by the architectural difference between bidirectional attention and autoregressive generation, which turns the model into an elite code reviewer who spots every fallacy in classification, but a junior dev who commits all of them when generating text from scratch.
It forces a profound shift in how we engineer systems around these models. We have to stop treating them like deterministic state machines that execute rules.
And start treating them like highly educated, highly biased, probabilistic guessers that require immense scaffolding and validation.
Exactly.
And the sources tease that this exploration of logic is just the first layer of the LLM mastery deep dive. Now that we have mapped out the boundaries of deduction and probability, the next frontier they cover is causal reasoning, counterfactual thinking, and common sense.
Those areas represent an entirely different kind of hurdle.
Oh, absolutely. The intuitive physics, the understanding of cause and effect, the ability to imagine hypotheticals, the exact things you do effortlessly while making that cup of coffee, they remain profoundly, almost intractably difficult for an architecture that only understands the world through the statistical proximity of text tokens.
It's going to be a fascinating follow-up.
Definitely. Which leaves us with a lingering thought for you to mull over as you turn back to your IDE, clear your terminal, and write your next prompt. If LLM logic is primarily statistical correlation derived entirely from human text,
Right.
and we know that human text is inherently riddled with the content effect, cognitive biases, and logical fallacies, are we actually trying to build machines that are perfectly logical? Or have we, in our pursuit of artificial intelligence, accidentally engineered computational mirrors that are perfectly convincingly flawed, just like us?